There is a single number that comes out of Einstein's equations when you describe a black hole. And when physicists applied that same number to the entire observable universe, the mass, the radius, the density, it matched. Perfectly. Not approximately. Not close enough to be interesting. Exactly. The universe fits the mathematical definition of a black hole. Every condition required. Every threshold satisfied. And the scientists who noticed this did not announce it loudly. They published it quietly, in careful language, surrounded by caveats. Because the implication is one that nobody in the field is comfortable saying out loud. If the math is right, and so far nobody has shown it is wrong, then we are not outside looking in at black holes. We are inside one. We have always been inside one. And the universe we think of as everything that exists is sitting on the interior of an event horizon that we will never see, never reach, and never escape. This is not a metaphor. This is not a philosophical thought experiment. This is what the numbers say. And the numbers do not care whether we find it comfortable. Let's start with what a black hole actually is. Not the dramatic version. The mathematical version. A black hole is defined by one thing, the relationship between mass and radius. If you take any amount of mass and compress it into a small enough volume, the escape velocity from its surface exceeds the speed of light. Nothing can leave. Not matter, not energy, not information. The threshold radius for this to happen is called the Schwarzschild radius, named after Karl Schwarzschild, who derived it in 1916 while serving on the Russian front in World War I, sending the calculation to Einstein from a battlefield. The formula is clean. Radius equals 2 times Newton's gravitational constant times mass, divided by the speed of light squared. That is it. You plug in the mass, you get a radius. If the object fits inside that radius, it is a black hole by definition. No exceptions. No other conditions required. Now, take the observable universe. The mass of everything we can detect. Every star, every galaxy, every cloud of gas, every atom we have measured or inferred. Approximately 10 to the power of 53 kilograms. Plug that into the Schwarzschild formula. You get a Schwarzschild radius of approximately 13.8 billion light-years. The actual radius of the observable universe is 13.8 billion light-years. The number that falls out of the formula is the number we measure when we look as far as physics allows us to see. This is either the most extraordinary coincidence in the history of science, or it is not a coincidence at all. Before you dismiss this as numerology, consider what it would take for this to be a coincidence. The Schwarzschild radius depends only on mass. The observable universe's radius depends on how long light has had to travel since the Big Bang, a completely separate physical quantity governed by the expansion rate, the composition of the universe, and the history of dark energy. These two numbers, one coming from gravity, one coming from cosmology, have no obvious reason to be the same, and yet they are. Physicists have a name for this. They call it the Schwarzschild coincidence, and it has been sitting in the literature for decades, largely undiscussed in mainstream science communication because the implication is one nobody wants to state plainly. If we are on the interior of a black hole, then there is an exterior, a larger space, a parent universe in which our black hole formed and exists, a universe that, from the outside, sees our entire cosmos as a singularity, as a point, as a nothing, and from inside which our 13.8 billion year history, our 93 billion light-year observable volume, our 2 trillion galaxies, are just the contents of a collapsed object that some external physicist might study with instruments we will never see. Here is where the physics gets stranger. Because when you study what happens inside a black hole according to general relativity, you find that the interior operates by different rules. Outside a black hole, you have freedom of movement in space and flow in only one direction through time. Inside the event horizon, those two things swap. Space becomes the locked dimension. Every direction in space points toward the singularity. You cannot move away from it any more than you can move backward through time. And time, the dimension you normally have no control over, becomes something you can move through in multiple directions. Past and future become spatial concepts. The singularity is not in your future the way death is in your future. It is below you the way the floor is below you. Inescapable not because of destiny, but because of geometry. Now, if we are inside a black hole, then we are inside exactly this kind of space. The Big Bang is not the beginning of time in the normal sense. It is the boundary of our geometry, the thing that the equations place below us rather than behind us. And what exists beyond the event horizon, in the parent universe where our black hole formed, operates by rules we cannot point to. Time there flows in a direction we cannot describe. Space there has a freedom we cannot experience. We are inside the interior, and the interior, by definition, is the place from which nothing escapes. In 1992, a physicist named Lee Smolin published a paper that took this seriously. Not as speculation, as a testable scientific framework. The theory is called cosmological natural selection. The core idea is this: every black hole that forms inside a universe creates a new universe on its interior, a baby universe, separated from its parent by the event horizon, beginning with a Big Bang of its own, evolving with physical constants that are slightly mutated from the parent's constants. This is not arbitrary. Smolin proposed specific mechanisms by which the constants, the masses of particles, the strength of forces, the cosmological constant, could be transmitted from parent to child with small random variations, in a process structurally analogous to biological reproduction with mutation. And then he asked, if this is happening, what would we expect to observe? The answer is elegant and uncomfortable. A universe that produces the most black holes passes on its constants most frequently. Over many generations of universe reproduction, the constants would be selected for toward values that maximize black hole production. And the constants of our universe, when you examine them, are extraordinarily well tuned for exactly that. The mass of the proton, the strength of the strong nuclear force, the value of the cosmological constant, all sit near values that maximize the formation of stars, which collapse into black holes, which create new universes. Smolin made a prediction. It should be impossible to change any of our fundamental constants without reducing the number of black holes our universe produces. So far, every attempt to falsify this prediction has failed. There is a piece of this that connects directly to something we already accept as standard cosmology: inflation. The theory of cosmic inflation, developed by Alan Guth in 1981, and now the dominant paradigm for explaining the early universe, proposes that the universe underwent a period of exponentially accelerating expansion in the first tiny fraction of a second after the Big Bang. In less than 10 to the power of -32 seconds, the universe expanded by a factor of at least 10 to the power of 26. This expansion was driven by a field with negative pressure, a vacuum energy that caused space itself to accelerate outward. Inflation explains the flatness of space, the uniformity of the cosmic microwave background, the specific pattern of density fluctuations that seeded all large-scale structure. It is not fringe, it is the consensus. But here is what is rarely said clearly. Inflation, in most of its formulations, is eternal. It does not stop everywhere at once. It continues indefinitely in most of space, with small regions occasionally undergoing the transition from the inflationary phase to a normal expanding universe. Each such transition creates a bubble. Each bubble becomes a new universe. Each bubble is separated from every other by an exponentially expanding background it will never cross. Each bubble is, in the most technical sense of the word, causally isolated from everything outside it. Causally isolated. Surrounded by a boundary nothing inside can cross. In the leading mathematical formulations, inflation and black hole interiors are the same object described from different perspectives. From outside, a black hole. From inside, an inflationary universe beginning its expansion. The two descriptions are mathematically equivalent, not similar, equivalent. Now bring in quantum mechanics. Because classical general relativity says the interior of a black hole ends at a singularity, a point of infinite density where the equations break down. But physicists do not believe singularities are real. They are a sign that the theory is incomplete, not that reality becomes infinite. Quantum mechanics must intervene at some scale, and when it does, the singularity does not appear. Loop quantum gravity, one of the leading approaches to quantizing gravity, predicts that the singularity inside a black hole is replaced by a quantum bounce. The collapse reaches maximum density at the Planck scale, the smallest meaningful length in physics, and then rebounds. The compression reverses. The interior expands outward, a collapse on one side, an expansion on the other. A black hole from the outside, a big bang from the inside. The interior of every black hole in our universe may be a new universe in the process of beginning. And our own Big Bang, from the perspective of whatever exists outside our event horizon, looks exactly like what we see when we observe a black hole in our universe. A collapsed point, a singularity, an object that absorbs everything that falls in and reveals nothing of what happens inside. We are the inside, and the inside looks, to us, exactly like a universe. Stephen Hawking showed in 1974 that black holes are not entirely black. Quantum effects near the event horizon cause them to emit thermal radiation, a slow leak of energy that carries no information about the interior. Over an astronomical span of time, a black hole radiates away its entire mass and evaporates. This created a crisis. If information cannot escape a black hole, and if the black hole eventually evaporates, then the information about everything that ever fell in is destroyed. This violates a fundamental principle of quantum mechanics, that information is always conserved. This is known as the black hole information paradox, and it remains one of the deepest unsolved problems in theoretical physics. Now apply it to our situation. If we are inside a black hole, then the information about everything that happens inside our universe, every particle, every event, every measurement, every thought, is being encoded on the event horizon surrounding us. This is what the holographic principle says. The interior of a black hole is entirely described by a two-dimensional surface at its boundary. Our universe, in this framework, is not three-dimensional in any fundamental sense. The three dimensions we move through are a projection from a two-dimensional surface we will never reach. The event horizon of our parent black hole encodes everything about us. From the outside, a physicist in the parent universe could, in principle, read the entire history of our cosmos from the quantum state of our horizon. They would not see stars. They would not see galaxies. They would see the surface of a black hole. A membrane, a thermodynamic object. We are the content. The horizon is the record. And the record is kept by someone we will never know. There is a version of this that offers a specific and testable structure. Most black holes are expected to rotate. The matter that falls in carries angular momentum, and conservation of angular momentum means the black hole spins. A rotating black hole is described by the Kerr metric, and its interior is different from the non-rotating case. The singularity inside a rotating black hole is not a point, it is a ring. And the geometry around a ring singularity includes regions where the equations permit movement in any direction through time. Now, if our universe formed inside a rotating black hole, as most real black holes are expected to be, the initial conditions of our universe would carry the imprint of that rotation. The spin of the parent black hole would have seeded the angular momentum budget of everything inside. And there is an observation. The universe has a preferred handedness. Spiral galaxies are not randomly distributed between left-handed and right-handed spirals. Studies examining very large samples have found a statistically significant excess of galaxies with one specific rotational direction. Small, debated, not yet confirmed beyond all doubt. But if it holds, it is exactly what you would expect from a universe born inside a rotating object. A faint fossil memory of the spin that created us, written into the rotation of 100 billion galaxies across hundreds of millions of light years. Here is something that connects to a real, active, unresolved crisis in modern cosmology. The Hubble tension. The Hubble constant describes how fast the universe is expanding. Two independent methods of measuring it give answers that disagree. Not by a small margin. By enough that statisticians say the probability of this being random is less than 1 in a million. The early universe measurement gives approximately 67 kilometers per second per megaparsec. The local measurement gives approximately 73. This has been confirmed by multiple independent teams using different instruments. It is not going away. Most cosmologists believe it signals new physics, something in our model that is wrong or incomplete. But there is a subset of physicists who have noted something specific. In the cosmological black hole framework, the expansion rate of the interior universe is not a free parameter. It is set by the conditions of the parent universe at the moment of black hole formation. If our universe's expansion rate was determined by conditions in a parent universe we cannot observe, then the tension between early and late measurements might not be pointing at new particles. It might be pointing at a seam, a place where the interior geometry transitions, subtly, from what was set by the parent to what is driven by our own physics. A transition we are only now sensitive enough to detect. A scar from the birth event, written into the expansion of space, finally visible after 13 billion years of dilution. There is a further thread that deserves to be pulled. The cosmic web, the large-scale structure of the universe, looks like something when you step back far enough. The filaments of dark matter and gas connecting galaxy clusters with vast voids between them. This pattern was noticed by a team of cosmologists in 2020 who compared it to the structure around accreting black holes and found the match statistically significant. The voids between filaments resemble the regions of space just outside the ergosphere of a rotating black hole. Nearly empty, dynamically quiet, surrounded by the active structure of the boundary region. The filaments themselves, the sheets and threads of concentrated mass, resemble the accretion structures that form around compact objects. These researchers were careful. The language was measured. But the observation is in the literature. The large-scale structure of the universe maps onto the exterior geometry of a rotating black hole when compared at the correct scale. And this raises the question that no standard cosmological model currently answers. Why does the large-scale structure look like this at all? The standard answer involves initial density fluctuations amplified by gravity over time. But the specific geometry of the result, the particular topology of filaments and voids, has features that match the boundary geometry of a black hole better than any random gravitational collapse model predicts. We may be reading the shape of our container in the arrangement of the matter it contains. Here is the detail that stops most physicists from dismissing the black hole cosmology entirely. The flatness problem. The universe is, to extraordinary precision, spatially flat. The curvature of space, measured from the density of matter relative to the critical density, is within 1% of zero. This is strange because a universe that begins with even a tiny deviation from flatness will either collapse or expand to near vacuum extremely quickly. For the universe to still be this close to flat after 13.8 billion years, the initial conditions would have to have been fine-tuned to incredible precision. Inflation explains this. Exponential expansion smooths out any initial curvature. But black hole cosmology offers a different explanation. The interior geometry of a large enough black hole, in certain quantum gravity models, is naturally flat. Not because of fine-tuning, because the collapse process itself sets the initial conditions to near-flat geometry. Flatness is not a coincidence in this framework. It is a feature of the birth channel. The imprint of an exterior structure we cannot see, written into the shape of a space we move through without knowing where it came from. When you ask why the universe is flat, the standard answer is, inflation made it so. The black hole answer is, it was born that way. And the two answers are, in the leading mathematical frameworks, the same answer wearing different clothes. Let's be honest about what is established versus what is inferred. The Schwarzschild radius coincidence is real and confirmed. The mathematical equivalence between inflation and black hole interiors in certain frameworks is real and published. Smolin's predictions have not been falsified. The holographic principle is accepted by a majority of theoretical physicists. The flatness and homogeneity of the universe are consistent with interior black hole geometry. None of this, individually or together, constitutes proof. The standard cosmological model fits the data without requiring an exterior context. You can do all of standard cosmology without ever invoking a parent universe. But here is the thing about physical theories. They do not require universal acceptance before they deserve serious examination. They require that the mathematics works, that the predictions are not falsified, and that the framework offers explanations for things we cannot otherwise explain. On all three counts, black hole cosmology is not eliminated. It is alive. It is in the literature. The physicists who take it seriously are not fringe scientists. They are people who did the calculation and found the number came out right. The Schwarzschild radius of the observable universe is the observable radius of the universe. That is the fact. Everything else is an argument about what that fact means. And here, at the end, is the most disorienting implication of all. If we live inside a black hole, if the universe is the interior of a collapsed object in apparent space, then the end of our universe is not an end. It is a transformation. The heat death, the maximum entropy state toward which the universe is evolving, where all gradients are gone, all structure dissolved, all black holes within our universe have themselves evaporated. That is not the termination of existence. From the perspective of the parent universe, from outside our event horizon, none of this ever happened. The parent observer sees only the surface, the thermal glow of a black hole slowly radiating for however long their physics measures as the lifetime of such an object. They do not see the stars. They do not see the galaxies. They do not see 13.8 billion years of history. They see a point of concentrated mass, slowly radiating, eventually gone. Our entire existence, every civilization that ever arose, every measurement ever made, every question ever asked, is a thermal fluctuation on the surface of an object that an external physicist might study as a homework problem. We are the interior. We are the answer to the question of what happens inside. We are what the singularity became when the quantum bounce replaced the collapse with expansion. We are the inside of the thing that swallows everything and returns nothing. And somewhere, in a universe whose physics we cannot know, on instruments whose principles we cannot imagine, a scientist is looking at the horizon surrounding our entire existence and measuring its temperature. And finding it, as expected, exactly what the formula predicts. Cold, quiet, almost imperceptibly warm, and completely, perfectly, mathematically consistent with the thing it contains.